Assalamu alaikum and good evening, everyone. Today we are going to start uh, IGCSE May-June 20 paper 2 alternative to practical. Question number 1. Hot powdered lead-2 oxide is reduced by methane. A flammable gas. Okay, so how hot powdered lead-2 oxide, lead-2 oxide means PbO, is reduced by methane, which means it is reacted by methane. A flammable gas. Okay, so they are telling you that methane is a flammable gas. The products are lead, steam, and carbon dioxide. So it means lead. Steam means H2O in a gaseous state. And carbon dioxide. Okay. Okay. So from here, the methane gas is introduced. Here we have a lead oxide. So when methane gas comes in contact over here, the reaction occurs and the products has been formed. And as a result, uh, we'll get a lead over here, water over here, and carbon dioxide. Okay. Name the item of apparatus labeled A. So yes, what is A? Yeah, it's a beaker, right? Very good. It's a beaker. Now, draw an arrow on figure 1.1 to show where the apparatus should be heated. So basically here we have a solid. So we have a we have to put the arrow over here because this area must be heated. Flammable means that it catches fire, Shaya. Okay. So this area must be heated. So as when the gas comes in contact with the hot lead-2 oxide, the reaction occurs readily. Okay. Now, next part. Explain why powdered lead-2 oxide is used, not a large lump of lead-2 oxide. So we know that powder has larger surface area, hence reacts faster. Yeah, faster rate of reaction. Very good. Now, B part. Explain what happens at the point labeled B on figure 1.1. So, if you see at point B, what will happen that you see that the products are lead, steam, and carbon dioxide gas. So, steam and carbon dioxide gas reaches over here, and as a result, there is a ice. So, due to the ice, the steam condenses to form a liquid and turns into ice, and the carbon dioxide moves and go over here. So at point B, uh, I'll write that at point B. Just give me a minute, please, everyone. Okay. So no, lead is not going to be collected at B because lead is a solid. So this is the solid. So when the methane comes in contact, this solid actually turns into lead. So there is no movement of a lead. Okay, only methane and water moves over here. So at point B, ice cools the steam and steam condenses to water. Yes, the thing is that the lead oxide is solid over here, right? So when methane comes in contact, because methane is a gas, right? So on reaction from here, steam and carbon dioxide gas escapes, and this is the lead oxide, which turns into lead metal over here in this region because it's a solid, so it doesn't move, okay? Okay. So at point B, there is ice. So ice, when the steam reaches, the ice cools down the steam, and as a result, the steam condenses and turns into water. E. The waste gases contain methane. So just why the waste gases should not be released into the laboratory. Uh, so as we have, they have mentioned over here that in the start that we about a methane that it's a flammable gas. So that's why we cannot, release them into the laboratory, because if someone no, methane is yeah, it can catch fire. Not that it's not toxic. You can write that it can catch fire. That's why we cannot release them uh into the laboratory. Methane is flammable, hence catch fire. Okay. Now question number 2. A student investigates how the rate of a reaction between aqueous iron 3 nitrate and aqueous sodium thiosulfate changes with temperature. So see, they have given you the objective that what is the purpose of the investigation, to see the difference in the rate when there is a different temperatures, and the reaction is between iron 3 cell nitrate and sodium thiosulfate. These two are the reactants. The student does 5 experiments using the apparatus shown in figure 2.1. So see, it's a 100 centimeter cube beaker. It contains 50 centimeter cube of iron 3 nitrate and 5 centimeter cube of aqueous sodium thiosulfate has been added, and the student is looking at this solution from the top like this. Okay. And here in there is a printed text. So what will happen that the solution turns cloudy, and as a result, the print disappears from the top view, and the student note the time, that in how much time it disappears. No, Khatija, read the question carefully. They are saying that the waste gases contain methane, right? So it means some of the methane is not used up. Okay, now in experiment 1, use a 50 centimeter cube measuring cylinder to pour 50 centimeter cube of sodium nitrate into a 100 centimeter cube beaker. Stand the beaker on a printed sheet on a figure as shown in figure 2.1. Use a 10 centimeter cube measuring cylinder to pour 5 centimeter cube of aqueous sodium thiosulfate into the beaker, and at the same time start a stop clock. Okay. Use a thermometer to stir the content of the beaker. Look down from above the beaker, and when the text on the printed sheet becomes visible, stop the stop clock. Okay. Use the thermometer to measure the temperature of the solution when the text becomes visible. Okay. Rinse the beaker and thermometer with the water. The experiment one is clear to all of you. Now, so we are noting down the time and we are noting down the temperature as well. Now, what did this in what have the student did in experiment 2? Use the 50 centimeter cube measuring cylinder to pour 50 centimeter cube of iron 3 nitrate into a 100 centimeter cube. Heat the beaker on a gauze over a Bunsen burner until the temperature of the iron 3 nitrate has increased by 5 degrees Celsius. So see here, there is no heating. So the reaction occurred at 5 degrees Celsius lower temperature, right? Okay. Stand the beaker on the printed sheet as shown in figure 2.1. Use the 10 centimeter cube measuring cylinder to pour 5 centimeter cube of aqueous sodium thiosulfate into the beaker, and at the same time start a stop clock. Use the thermometer to stir the content of the beaker. Look down from above the beaker, and when the text on the printed sheet becomes visible, stop the stop clock. Okay. Use the thermometer to measure the temperature of the solution when the text becomes visible. Rinse the beaker and thermometer with water. So see, we are recording the time and we are recording the temperature as well. Now experiment 3, repeat experiment 2, this time heating the aqueous iron 3 nitrate until the temperature has increased by 10 degrees Celsius. So in experiment 1, it's at room temperature. In experiment 2, 5 degrees Celsius higher. In experiment 3, 10 degrees Celsius higher. In experiment 4, repeat experiment 2, this time heating the aqueous iron 3 nitrate until the temperature has increased by about 15 degrees Celsius. Okay. Now, in experiment 5, repeat experiment 2, this time heating the iron 3 sulfate until the temperature has increased by 25 degrees Celsius. Okay. So, if you see over here, it is, for example, if this reaction occurs at room temperature, this reaction occurs at plus 5 degrees Celsius, this reaction occurs at plus 10 degrees Celsius, then 4 occurs at plus 15 degrees Celsius, and 5 occurs at plus 25 degrees Celsius. Is this understandable to all of you? Okay. Now, we got the stop clock diagram. If you see over here, time taken for the text to become visible, temperature of the solution when the text become visible. So the temperature of the solution when the text So if you see the temperature is over here, it's 21, 22, 23. So it's between 20 and 21. So it is going to be 20.5. The temperature over here is 27. The temperature over here is 30.0. The temperature over here is, if you see, 37.0. And the temperature over here is 46. And it's between 46 and 47. So it's 46.5. Okay. So we noted down the temperature. Now, we have to record the time in seconds. So if you see, this is minutes. The inner dial is minutes and the outer dial is about seconds. So if you see over here, it is 1 minute, right? So if it's a 1 minute over here, which means it is going to be 60 seconds because we have to record the temperature in second. And if you see the other minute, it is going to be, if you start, it is going to be 55 seconds. So 60 and 55 seconds. So if you add 60 plus 55, you are going to get 116 seconds. So here I am going to write 116 seconds. Is this understandable to all of you? Okay. Now the second one, if you see, here we have a 1 minute, which means 60 seconds. And here we have 20 seconds, right? So 60 plus 20 gives you 80 seconds. So experiment 2, which is at 5 degrees Celsius higher. 1 minute, Rahim. It's going to be 80 seconds. See over here, if this needle is greater than 1 and below than 2, so it means 1 second has been passed, right? And for that 1 second we are, oh sorry, 1 minute has been passed, and for that 1 minute I got this 60 seconds. But if you see the bigger needle, when it reaches over here, it is going to be on this point, which makes it 2 whole minutes, but it's lower than 2. So after 1 minute, how many seconds are passed? 55 seconds are passed. 120 will be when this needle would be over here, then it means it is more than 2 minutes. So it means 22 minutes. So it is going to be 120, and whatever the seconds, I will add 120 over there with that. But here, if you see, this needle is still below 2, which means 1 whole minute has been passed and this much second has been passed. Is it clear now? Rahim, Waleed? Okay. Now, if you see over here, 60 seconds, and over here 9 seconds. So it is going to be 69 seconds. Then over here, no minute, there is 0 minute. And if you see, 46 seconds. So I'm going to write 46 over here. Then it's 21 seconds only. So I'm going to write 21 over here. Is this understandable to all of you? Okay. Now, write a suitable scale on y-axis and plot your results from experiment 1 to 5. On figure 2.2, draw a smooth curve of best fit. Okay. Time taken. So if we see, we have a maximum time of 116 seconds, right? So if I mark this 0 and this as a 20 seconds, no, 1 minute, 10, 20. No, we have a maximum of 116 seconds, okay? No, then 20, 40, 60, 80, 100, and 120 seconds. Okay. So temperature of the solution when text becomes visible. So the first reading is at 20.5 degrees Celsius and the temperature is 106. Oh, the time is 106. So 20.5 means it is going to be over here, because if you see one scale unit represents one small box represents 1 unit. So it's going to be 20.5, and over here we need 116. So it is going to be 110. So 112, 100 and sorry, 112, 100, 116. So we are going to plot a point over here for 116 at 20.5. Now, the next one, if you see 27 and 80 seconds. So 27 would be this one, and on this one, we need 80 seconds. So it is exactly going to be over here. Remember, always plot the points with the, process, not with the dots. Then at 30, it's 69 seconds. So this is 30 and 69 is going to be over here. Okay. Then at 37, it's 46. So 37 is over here and 46. So 40, 42, 44, 46. So 46 is going to be over here. Then at 46.5, it's 21. So 46.5. So 46, 46.5. And the time is 21 seconds. So at 46.5, 21 is going to be over here in the middle of the box. So see, we got this. Now, you have to draw, if you see the instructions, read the instruction, draw a smooth curve of best fit, right? So the smooth curve of best fit so let's move. So it would be like this, okay? Okay. Now what they are saying, Reduce the experiment in which the rate of the reaction is fastest. So if you see the rate of the reaction is fastest is the one which takes the lesser time. So if you see, this is the experiment which takes the least time, and it's experiment number 5, right? So in experiment number 5 is it completed in 21 seconds. Yes, yes, all the points must be on the line, but there is a little variation in it. So I'm going to write experiment number 5. Now, use your graph to predict the temperature of the solution when the text becomes visible after 55 seconds. Show you're working on figure 2.2. Okay, so at 55 seconds, we have to identify. So if you see over here, this is going to be 50 and this is going to be 55. So on 55, I'm going to drop a straight line over here. So if you see, it's 33.5. So the temperature would be 33.5. Is this understandable? Yes, very good, Amal. Okay, now E part. Explain why wrapping the beaker in a cotton wool after it has been heated will improve the accuracy of the results obtained. Okay, it is because uh, it lowers the loss in heat due to insulation, obviously, because we have wrapped it with a cotton wool, it insulated, and as a result, less heat would be, loss. Hence, temperature change would be less. And as a result, it becomes more accurate. Yes, yes, very good, Amal and Khatija. Now, part F1. Explain why it would be an improvement to measure the volume of the aqueous iron 3 nitrate in a burette rather than a measuring cylinder. So it's very easy. If you guys recall, that's what I have discussed in the last class, that burette is a more accurate, right? And flour and measuring cylinder is for the approximate readings. So burette is more accurate than measuring cylinder. To suggest why it would not be an improvement to add the aqueous sodium thiosulfate using a pipette. Just give me a minute, please. Just a minute, please. Okay. Okay. Suggest why it would not be an improvement to add the aqueous sodium thiosulfate using a pipette. Okay. Yes. Sodium thiosulfate is, I think, with the, 5 centimeter cube has been added with the measuring cylinder. But the thing is that we are recording the time, we are measuring the rate. So if we add it with the pipette, pipette, from the pipette, the solution release very slowly. So when some of the amount has been added, the reaction has started. And you have to wait till all the solution would be transferred into the beaker. So that's how it will not work for the thiosulfate. Because when you are adding it, during the addition of the thiosulfate, the reaction would start. Because from the pipette, the solution is added slowly. By a pipette, solution was added slowly. So during the addition, it start to react. Yes, pipette is more accurate, but I didn't say that pipette is more accurate than burette. Pipette and burette both are accurate, and measuring cylinder is, for the approximate measurements, but pipette and burette both are for accurate measurements. Okay. Now, suggest why the aqueous sodium thiosulfate must be added after aqueous iron 3 nitrate has been heated and not before it is heated. So the same reason, if we mix both of them and start heating, so during the heating, the reaction would start. But we are mixing it after when we are achieving our target temperature that we need to raise, right? So after that, we add it quickly and then start the stopwatch. So here the answer would be same, that during the heating, reaction starts at lower temperature. See, for example, we need to raise the temperature of to 5 degrees Celsius. But when we add it and we are now heating and waiting till the temperature to reach 5 degrees Celsius. So it is very high possibility that after a raise of a 1 degree Celsius, the reaction starts to happen, right? So that's why we first heat it, we maintain the temperature, the higher temperature, and then we mix both the things. Is this clear to all of you? Now H. Describe how the results of the experiment would change when the experiment is repeated using a 250 centimeter cube beaker in the place of 100 centimeter cube. Explain your answer. No. Here, the time decreases, and time decreases means the rate increases. And why is it so? No, we are not increasing the volume. The volume is the same, but we just change the container. For example, initially you are performing the experiment in 100 centimeter cube container. And now they are saying that you are going to perform that same experiment in 250 centimeter cube container, right? And we are noting down the time when the it's again visible to see, right? So see, in this, the same volume have this much depth, right? But in this container, the same volume must have a very smaller depth. So it's very easy to look through it, right? So in 250 centimeter cube beaker, less depth of solution makes it to look through more quickly. Because we didn't change the volume of the solutions, right? If you see, we just changed the beaker. So when we use the 250 centimeter cube beaker, obviously its diameter is bigger. So the solution, which is, having a more height in the 100 centimeter cube solution. Yeah, you can say that. So the solution spreads in the bigger region. As a result, it will easy to look through it. Now, question number 3. So if you see this question number 3, a student has two substances, solution F and G. So it's from the test for cations and anions. Test on solution F. The table 3.1 shows the test and the student's observation for the solution F. The student divides the solution F into 3 portions. Okay. Test 1. Do a flame test on the first portion of the solution F, light green color. So if you see the light green color over here from the chart, you can able to identify it's barium, I suppose. Yeah, see. So from here, we got to know that barium ions are present, right? So F has barium ions. To the second portion of a solution F, add a 1 centimeter depth of aqueous sodium hydroxide and a piece of aluminum foil. Warm the mixture gently and test any gas. Effervescence was seen. The gas turns damp red, litmus paper blue. So it means that gas is ammonia, and that if it's an ammonia, it means that the F contains nitrate ion in it. If you see over here, yes, very good, Ahmad Mushtaba, and very good, Amal. Okay, so see over here. Here, for a nitrite ion, aqueous sodium hydroxide, aluminum foil, warm carefully. Ammonia is produced, and this happens when there is a nitrate in the sample. NO3 minus. So we got to know that it has a nitrate ion. Okay, now test 3. To the third portion of a solution F, add a 1 centimeter depth of a dilute nitric acid followed by a few drops of silver nitrate. No change. So it means no halide ion, no chloride ion, no bromide ion, no iodide ion. Is this understandable? Okay. Now describe how to do a flame test using test tube in test 1. So if you recall, make a wire loop. Take some crystals on it, right? And put into a blue flame. The crystals of the sample F, see, they are saying that that is a solution F. So we will take that sample in it. Okay, and it's a solution. Yeah, right. 1 minute. So 1 minute. Make a wire loop. Dip it in solution. If it's a solid, then you can write that. And put it into a blue flame. Okay, and if there is a solid, then we take the crystals by dipping or by immersing that wire loop into that solid. B. Identify the gas given off in test 2. So we have identified in a gas test 2, ammonia gas has been given off. Identify solution F. So we have identified that the solution have a barium ion and the nitrate ion. So if there is a barium ions, Umar, is this clear to you? So we are going to get barium nitrate as barium ions and nitrate ions are present. Okay. State what would be observed if the student add dilute sulfuric acid to another portion of a solution F. There is a barium ions, right? Yes, very good, Amal. White precipitates. See over here, Khatija, it's light green color. If you see over here in the flame, see flame test, barium ions, right? Yes, so if the barium ions are there and we are adding the sulfuric acid, so it would form barium sulfate, which has a white precipitates. So the observation over here is white precipitates. Now, test on solid G. Solid G is iron 3 carbonate. About 10 centimeter cube of dilute sulfuric acid is added to solid G. Any gas given off is tested. Okay, so we know that it's a carbonate. So it means which gas is going to be tested? Carbon dioxide. And how we can the gas is carbon dioxide, and how we test it? Test this. So the first observation is bubbles of colorless gas, because the gas has been formed, so you are going to observe the bubbles or the effervescence. Then the test for the gas, as we know that it's carbonate, so the gas is carbon dioxide, so pass the gas through lime water, it turns milky. Part F, to the product from E. Okay, aqueous sodium hydroxide is added dropwise until in excess, so it has the iron 2 positive ions, right? So adding dropwise, what we are going to get for iron 2 positive ions? Green precipitates. Yes, very good. And these green precipitates are insoluble. Yeah, it's insoluble in excess. Now, question number 4, the designing part. A metal polish is a mixture of 4 substances. The properties of these substances are shown in table 4.1. Okay, propanol, soluble in water, reaction with dilute nitric acid dissolves. Okay, iron 3 oxide and silicon 4 oxide insoluble in water, reacts with when warmed to form soluble salt. Okay, and it does not react with the acid. Plan an experiment to find the percentage by mass of silicon 4 oxide in the mixture. Your plan should include how you will calculate the percentage of silicon 4 oxide in the mixture. You provide with the sample of the metal polish, dilute nitric acid, and a common laboratory apparatus. So first thing, we must have a known mass of a polish. Yes, very good, Amal. So record the mass of sample metal polish. So you know its mass, right? Now, afterwards, what you are going to do? You are going to add dilute nitric acid in it. So what will happen? On adding dilute nitric acid, and from the metal polish, all the propanol dissolves in nitric acid, and all the ethanoic acid also gets dissolved in nitric acid, right? So add dilute nitric acid in a container having metal polish. Now see, on adding this, they both gets dissolved in it. No, there is no need of water because on adding water, it stays insoluble, right? But when I added nitric acid, these two gets dissolved and it can be also get dissolved when I heat it. Now after this, what I will do? I'm going to heat the container. So what will happen on heating? On heating, see this iron 3 oxide also gets dissolved on heating, right? In it. So it means now the solid left is only a silicon 4 oxide. Is this understandable? So what we do next? So on heating the container, we get rid of the iron 3 oxide from the metal polish as well. Now that solid have only silicon 4 oxide. Filter to separate solid residue which is only silicon 4 oxide. Wash the residue and dry. Now record or weigh its mass. Now we got the mass of the silicon 4 oxide and we got the mass of the total sample initially, right? So how I'm going to calculate the percentage? Percentage of silicon dioxide is equals to mass of silicon dioxide over, yes, very good, total mass of metal polish times 100. And by this expression, I am able to calculate the percentage of silicon dioxide in the sample. Is this understandable to all of you? So here we are done with the paper. And tomorrow we are going to do another paper, inshallah. So see you everyone tomorrow. Take care. Goodbye. Allah Hafiz. No, it's silicon 4 oxide, not silicon 6 oxide. Yeah, you can write the short sentences, Amal. Okay, take care everyone. Allah Hafiz.